Welcome to this webinar where we're going to talk about ensemble models with Python. So we're going to focus on two techniques called bagging and boosting with libraries on Python that are called scikit-learn, XGBoost, and LightGBM. So this webinar, I'm hoping will take no more than 45 minutes, but it might be a bit longer. We'll see. Just a quick introduction before getting started. So my name is Kevin. I'm working at Cambridge Spark. What we do is multiple things at the intersection between education and data science. So we run a bootcamp in London where we're teaching students everything they need to know to be a data scientist. The bootcamp is a 6-month program. We're also doing content that we put online, such as this webinar. We also have tutorials on our website. We're also doing consulting for companies and organizing events as well. We have summits, data science summits in London, Manchester, and Cambridge. So if you're interested, check out our website. If you want to keep in touch, you can also follow us on Twitter. Right. So the agenda for today, we're going to start with a really quick introduction to bagging and boosting, which are the two techniques that that are used in the algorithms we're gonna use today. It's gonna be really short. So if you want to know more about those techniques, you'll need to find resources online after. And most of this webinar will be really applied. So I'm going to do some live coding using random forest, which is implemented in scikit-learn. So if you're familiar with the Python data science libraries, you probably have used scikit-learn before. And two other libraries, XGBoost and LightGBM, which are used a lot for machine learning competitions because they're really performant. So some prerequisite for this webinar. So everything I'm going to do is going to be with Python and in a Jupyter notebook. So it's good if you've used those before and if you're familiar. Otherwise, some things might be confusing. Same for a library called pandas that is used to manipulate data with Python. So I'm not going to explain everything I'm doing with pandas. So it's good if you have some background in it. If you don't, it's good as well, but some things might be a bit confusing. Also, it's good to be a bit familiar with what a decision tree is, because all the models I'm going to use are based on decision trees. So just put a picture here. Decision tree is really simple. You start from a node at the top where you're asking a question, and it can be either yes or no. And then you go down until you finally find an answer to the question. So it's here, for example, about a dog. So if you want to do the same thing at home, which would be really nice, you will need a few libraries. So I've listed here all the libraries you need to install. So scikit-learn, XGBoost, and LightGBM. Those are going to be the main libraries we're going to use. Also for visualizations, you will use matplotlib, which again, if you've done data science with Python before, you probably know it already. And graphviz, which is used to show decision tree, to plot decision trees. Right. So let's get started. Just a really quick introduction to bagging in random forest. What we want to do here is to build a set of models and ensemble them together, group them together. So we actually start with our data set, and from this data set we build as many samples of the data set as we want to. So here we've chosen, for example, to build an ensemble of 4 models. So what we're going to do is sample from the original data set with replacement, meaning that some of the initial observations will be duplicated. Some of them will be unique. So here in my sample one, I'm using the sample one, for example, to build a first model, then a second model, a third model, and I can do all of this in parallel. So the main thing to keep in mind here is that we building all those models in parallel, and then we aggregate them. So the idea here is that having several models that are trained on slightly different data is better than having one single model that would either overfit to your data or just not be that performant. So we prefer having several models that pick something different in the data and then get an average of those. If we're doing classification here, we'll take the majority vote from all the models as our final answer, or if we do regression, we'll usually take the mean. So here, just to keep in mind, we are building models in parallel. That's the general idea behind bagging. Random forest is just that, but with trees. So again, I'm just explaining really quickly the theory because I want to spend more time on using the libraries. If you want to know more about the algorithm, you can find a lot of resources online. Right. The second technique that we're going to see that is used by XGBoost and LightGBM. So the two other libraries we're going to use is called boosting. So here the difference is that we're not building several models in parallel. We are building them sequentially. So we start from our original data set. We build the first model. Then we are looking at everything that this first model got wrong. And for all those things that we got wrong, we are building a new data set that has more weight on everything that was wrongly either classified or predicted by the first model. So what we're trying to do here is build a new data set that will be used by another model to correct the error. Just to go through quickly, we have model one that is good at predicting something and bad at predicting other things. So when we're training our model two, we are making it on purpose good at correcting what the first model got wrong. So here, the main thing to keep in mind is that we do it sequentially and we correct the error step by step, meaning that if we have too many trees, we will really easily overfit. So that's something to keep in mind in practice. Just a quick word on how we aggregate those. So here we cannot just take the mean or the majority vote from all our models because only the model one is actually really good. The other models are just here to correct the error. So what we're going to try to do is put higher weights on the model one and then decreasing weights on the following models. The details of that can be found on when you're reading more about the algorithm online, but I'm not going to go through it here. It doesn't really matter for the purpose of this webinar. Right, so that was probably the shortest introduction ever to bagging and boosting. Oh yeah, and again, XGBoost and LightGBM will be using trees, so we could have used any model, but those libraries will be using trees. Right. So let's get started. Just a quick word about the dataset that we're going to use here. So you can download it at the following URL. It contains a list of posts that were posted on Facebook, and the idea is that we have 53 features describing each post. So it contains things like the number of likes, the category of the page where it was posted, etc. And the goal is to predict the number of comments that this post is going to have. Right, so let's get started. Can you guys see that? Right, good. No, there is a delay. Okay. Okay, good. All right, sorry, I was just waiting for for the thing to show up. Right, so first step is to actually load the dataset. Oh, no, first step is to actually download the dataset. So you can have it following the URL that I showed on the right here. So you have data folder here, and you have description of all the features. We'll get back to it after. Right, so first, let's import pandas to be able to read our CSV. So you will need first to unzip it. And then if we go here, you'll see that there are actually several CSV. We've chosen to use the first one. It doesn't have any headers, so we need to specify the option header equal none. And then we want to create some names. So what I've decided is to call all the features X something. So here I'm going to do X, X1, X2, up to X54, which is going to be our target here for I in range 1 to 55. All right, and I'm calling this data frame df. So if I have a quick look at the shape of the f, I have 40,000 rows here, so quite a lot of data to start with. And I can look at how it looks like. So I have all my features here. You see that head is not really helpful here because the data set is already sorted. So pretty much all the first rows are really similar. So what I'm going to use instead is sample that allows me to take rows randomly. And yeah, it's much more helpful. Right. So let's now extract the data and the target from this data set. So I'm calling X the first 53 features. So it's starting at index 0. So index 0 up to index 52. So I'm putting up to index 53 since it's not going to be included. And finally, the target is going to be the 54th feature. So here, if I just check X, Y, X. Now, once I've done that, I'm going to split the data set into a training set and testing set. So in order to do so, I'm going to use a method that is defined by scikit-learn in model selection, which is called train. Which is called train test split. And what that does is exactly what you would expect. I'm passing my features X, my target vector Y, and I'm defining what size I want for my test data set. I'm also adding a random state here because I want the same. I want to be able to replicate that analysis here, and it's returning X train, X test, X Y train, and Y test. So you need to have the order right, but basically it's returning the training, the features for the training set, the features for the testing set, then the target for the training set, the target for the testing set. All right, so we're good to go. Now we can start tuning and training random forest on this data. So what I'll use here is first the grid search method from scikit-learn, which allows me to test my model with various parameters, so I can choose the best one instead of like writing a loop myself. And now I can also import from ensembles my random forest. So as you can see here, I have the choice between random forest classifier or the random forest regressor. So here I want to do a regression. So I'm loading the regressor. Right. So I've cheated a bit here because grid search can be really long to train and to find the best parameters. So I didn't want to do that live. So what I've done is I've already run it and I know already the best parameters. So I'm defining them here. So the parameters that we want to tune for the random forest are the following: the max depth and the mean sample split. Those are the most important. So the max depth is controlling the maximum depth of your tree. So from the top node up to the really bottom. The reason why we want to do that is if we don't, our trees can be like really deep and start overfitting to samples that are not really representative of your data. So we want it to generalize and only get the most important rules or nodes. The mean sample split is the same idea, trying to reduce overfitting by having constraining the number of observations to be there in your data to justify a split. So you can't create a new node if you don't have more than mean sample split observation in the following nodes. And then I have a certain amount of fixed parameters that I don't want to tune at the moment. So I've the most important here is the number of estimators. I've set it to 10. So as we've discussed before, random forest is gonna create several models in parallel. Adding more models will improve accuracy. So I can start with like only 10 models to try to find my best parameters, max depth and mean sample split. And once I have them, I can increase then the number of estimators to try to improve accuracy. I've also defined a random state here to be able to replicate, and njobs is just the number of CPUs I want to use. If you put -1, it's going to use all the CPUs on your computer, so you don't have to know how many you have. All right, so we're ready to start our grid search. So I define the first argument of the grid search is your base model. So I want to use the random forest regressor with my fixed parameters. So if you're not familiar with Python, what I'm doing here with the double star is unpacking that dictionary. So what it's going to do is defining all those arguments in the dictionary as parameters of the function random forest regressor here. Then I need to define my parameters for the grid. So those are gonna be all the parameters I'm gonna try. In this case, my list for each parameter I have a list of 1 element, so there won't be a lot of suspense here. But if you were to tune it yourself, you need to try more. I also need to define njobs again to use all my CPUs, and scoring. So what metrics I want to use to say that a model is better than another one. Here I've decided to use mean absolute error, which is the absolute difference between what you expected and what you got, which is interesting because it's in the same units as your target. So here the number of comments, so we'll be able to compare to interpret it more easily. The reason why there is neg here is because it's the negative one. The grid search is trying to maximize metrics. So if I want to minimize the absolute error, I need to maximize the negative absolute error. All right. So I'm ready to fit it. So I will fit it on X train and Y train. It's so you see here the star means that it's running, and once it's fitted, I'm able to find the best parameters. Well, here I'm not really surprised because I've tested only those those two parameters here. So I'm not surprised that those are the best ones, but that's the process you should go through. Once I have the best parameters, so those models were fitted on a subsample of the training set within the cross-validation function. So what I want to do is retrain again my model, but on the whole training set. So I'm going to create a new random forest model with my fixed parameters that are still the same, and I'm going to pass the best parameters from my grid search. Then I can fit again this model on the training set, on the whole training set. Right, and now I'm ready to generate predictions. Right, so I just use the .predict method on the x-test, and that gives me my my prediction from that model that I just retrained. Now, in order to test to calculate the error, I'm going to import a function in scikit-learn that is called mean absolute error. So I said already that I want to use mean absolute error as my metric here, and I'm going to check why my prediction against the best one. Right. So here, 3.62. So what that means is that on average, my prediction of the number of comments is 3.6 comments off. So that's an interesting interpretation. Now, what we can do is, as I said earlier, we're starting with only a few trees, a few models in our ensemble, and I want to do. I'm able to increase it later. So that's what I'm going to do here. Let's go back here and look at our fixed parameters. So in my fixed parameters, I have my number of estimators, that is 10. So let's see, for example, if we put 50 there, and we train this model again with the same constraint on the max depth and the mean samples split. So I'm training it again, and we'll see if it increases if it decreases the error. Right, so it's fitted. I'm predicting again and looking at my error. So you see that the error decreased a little bit here, from 3.62 to 3.59, which isn't a big improvement, but it improved a bit. So what I suggest is that if you want to improve that model, maybe like spend more time tuning it, because I haven't spent that much time, and also try to put more to increase the number of estimators. Right, so an interesting thing that you can do as well with those models once they're fitted is access all the estimators individually. So if I do .estimators, I find all my decision trees here. It's actually a list, so I can check how many of them are there. 50, as I expected. So let's say, for example, we want to select the first tree out of my ensemble. So I just take the index 0. Here I've written a really short script that you don't have to. I'm not gonna explain, but it's basically using the graphviz method that I mentioned earlier to plot my first tree. So just if you want to visualize each of the trees that you have in your model, and try to understand a bit what the algorithm is doing. So here you see that the tree is quite complex. I have a lot of nodes in there, so I'm just going to look at the one at the top, which is usually one of the most important. So X33 here. So actually, if I go to my documentation, and I check what X33 is. So it's the number of comments in the first 24 hours after the publication of the post. Right, so it's interesting to look at that. So if this number of comments is below 191, then I'm going to this node, etc. So it can be interesting to look at that. Another thing that you can do is looking at the feature importance. So this is a list of the importance of each feature in the same order as like your features. So it starts X1, X2, X3. So the best way to visualize that is to put it in a data frame where your index is equal to your columns. So you actually have the name of each of them. Let's rename the column importance instead of 0. Now we can also sort the values. We don't want it to be ascending but descending, right? And once we have that, we're able to do a bar plot by using dot plot with canned equal bar. A bit small, but we can pass the argument fig size, increase the size, and here we are. All right, so that's an interesting plot that we can look at. So it shows in descending order the importance of each of our features for our random forest. So we see here that the most important feature is X35. So if I check here, X35 selected time in order to simulate the scenario. So I'm not sure what that one means. But if I check the second one, X31, that's the number of comments in the last 24 hours. So yeah, you can also, if you ask once you've built your random forest what features matter, you can look at those things. Right. So that's it for the random forest. Now the next algorithm that we want to try is called XGBoost. So that's a gradient boosting algorithm. So let's import the library first. Yeah, what I wanted to explain actually before is that XGBoost comes with two APIs. So you have two ways to train and use the models. So one which is called the scikit-learn API, which allows you to do the exact same thing as I did before, the exact same process. So what I mean by that is that in order to train your model, you will need your data in a data frame. You will then instantiate your model, so whatever it is called. So it can be the random forest regressor, it can be the XGBoost regressor. So instantiate that model with the parameters you want. And then on this model, you can call .fit to train the model or .predict to predict on your data. And that's what we are doing. We are going to do here first. So from XGBoost, you can import a classifier or a regressor. So here again, we're gonna import the regressor. Again, here I cheated a bit and already fitted already found the best parameters. So here I have two parameters that are really similar to the one before. So max depth is actually exactly the same as before. Mean child weight is really similar to the mean sample split that we had before. Just instead of counting the number of observations that we want in each node, we're counting the total weight that we want in each node. Because as I was explaining in the short intro to boosting, we're going to put different weights on different samples. Here, you see that there is a third parameter that I absolutely need to tune for XGBoost, which is the number of estimators. Whereas for random forest, I could do the number of estimators separately, because I just can start for a small with a small amount of trees and increase it. For XGBoost, it's important to get this number right. If I have too few or too many estimators, I'm gonna either underfit or overfit. So it's important to get this number right, and I need to train it in my to tune it with the other ones. Here I already know that 7 is the optimal number. My fixed parameters as well. A short explanation of those. So I have the learning rate, which is some sort of step size, meaning that at each boosting tree that I'm adding that is supposed to correct the error of the previous tree, I can put a different weight on how much error they're gonna correct. If I put a big value there, I will need less trees to get my optimal model. If I have a low learning rate, I will need a lot of trees until I actually get the best model. But hopefully that would be more accurate, because I'm correcting only a little bit of the error each step instead of trying to correct everything at once. Again, I'm defining a random state here, so I'm able to replicate this. 2 other arguments that I haven't mentioned before, but the same way for random forest, we do sampling of the data in order to have trees that are not correlated with each other. We can do the same for boosting. So this just means that I'm gonna take for each new tree, I'm gonna train it only on 90% of the original data and on 90% of the features, instead of taking all the features and taking the risk to overfit to one of the features. And again, I have the number of jobs or CPUs that I'm going to use. I put -1 so that it uses all my CPUs, and hopefully it's faster. So let's create a new grid search for that. So here, my base model in my grid search is going to be the XGB regressor with my fixed parameters. I need to add my parameters for the grid, so those that I want to test. Here again, I have just one parameter for each. I just have one value for each parameter, so it's not going to be. I know already what results I'm going to get. The number of CPUs I want to use, and again, scoring, I want to use the negative mean absolute error. All right. Now, once I have my grid search all set up, I can fit it on X train and Y train. It might take a minute. Oh, it was really quick. And then I'm able to check my best parameters, which there is no mystery here. I have a max depth of 10, mean child weight of 10, and estimator 7. So again, here what I want to do is retrain a new model with those parameters on the whole training set. So I'm defining an XGB model, which will be using my XGB regressor class with my fixed parameters. And I will use the parameters, the best parameters from my grid search. Once I have those, I can fit it on the X train, Y train, and I'm ready to predict. So Y pred is equal to my XGB model predicts on my test set. All right, so let's check how well I'm doing. So Y pred, Y test. All right, so 338 here. So that's an improvement. I think we only got 360 or something like that for the random forest. So that's a slight improvement with the XGBoost regressor. Here you note that we are using only 7 trays to get this result. And yes, I wanted to show you as well that with you can also access some interesting insight into your model with XGBoost. So you can plot the importance using the method plot importance from the XGB package. So here you don't code it directly on your model, but you take it from the package and you pass your model in it. And yeah, here something that I'd recommend is to set the importance type as being the gain, because by default it's gonna use the frequency. So how many times your feature is used in your whole model. So let's plot that. As you see, it's really small. So what I want to do here is first defining a new feature, and I can plug it on my in my plot importance function by defining ax is for axis and GCA is for get current axis. So I'm basically plotting that figure of size 2010 for my plot importance. So here we can see the importance of all my features. So the most important feature is X31. If I look it up, that's one that we've seen before, the number of comments in the last 24 hours. Right, so that's some insights that you can get. XGBoost also has a plot tree method. So same thing, you're passing your model into that function. You need to specify the index of the tree, and you'll be able to plot any of your trees. For example, here I'm plotting the tree at index 0, so the first one. You'll see that you don't see much. That's because those trees are quite big, so we can try to also, again, define our own figure and plot it on it. But you won't see much more. I think the best way to visualize that is to actually save it to a PNG or SVG and open it in like an image viewer, because here, like, it's really hard to see in a notebook. I suspect you don't see much on the video, but trust me, it's there. Right. So now, where we go from here, we could. In order to improve that model, the thing we would like to do is decrease the learning rate and trying to have more boosting trees and see if it improves the overall accuracy. So what we could do is just going up here, changing the learning rate here, and trying to find the best number of estimators from there. But what I want to show you is that you can use the so-called native API from XGBoost to automatically find the best number of trees that you need. But first, I'm going to explain how the native API is different. So, as you remember, with scikit-learn, you needed your data to be in a data frame to be able to use it in your model. For XGBoost, the native API, you need to define what is called a D matrix, which is a data structure proper to XGBoost. Your hyperparameters then, instead of instantiating a new model, you will put your hyperparameters in a dictionary that usually we call params, and then you call the train function directly from the XGBoost library to train a new model, and it will return your new model. So you don't instantiate the model before with the parameters. You're directly training with given parameters with your data that is in a D matrix, and the number of boosting round here is your n estimators that we had before, and then the predict is working the same way. So let's go back to the notebook. So here first, as I said, we'll need to define D matrices. So you can do it like this. So the D matrix takes the first argument, which is your training data, your features, and it takes a label. So it contains both your X and your Y. And so I created D matrix for my training data. I created D matrix for my test data. Label equal test. Right. Here again, I've defined my parameters already. So you know the max depth, you know the mean child weight already. The ETA is the equivalent of the learning rate. It's just the new name of the learning rate in the native API. So here, instead of having 0.3, I've decreased it to 0.08. That seems a bit arbitrary. It's just a number that works well, that is that gives good enough result and is quick enough to train live during the webinar. So that's why I've chosen this one. Sum sample and call sample by tree, it's the same as before. And here I need to specify which metric to use and what I want to do. So here, regression. Right. So a really handy method from XGBoost when you're using the native API is the cross-validation. So they have implemented their own cross-validation, which allows you to find the best number of trees needed. So let's create a new cross-validation object that takes first your parameters, so your dictionary that I've defined above. It needs to take as well your training set. You need to define which metrics you want. So here I'm interested in MAE. You need to specify, and that's one of the most important things to specify in this function, early stopping rounds. So what it's doing here, instead of testing different values of the number of trees you want to build, or instead of knowing it in advance, what it's going to do is sequentially build all the trees. And for example, if I put early stopping round equal 10, if accuracy hasn't increased, it's going to run a cross validation for at each stage. And if your score hasn't increased for 10 rounds, for example, it will stop training and just return the best number of trees. So that's just using the fact that it's a sequential algorithm. So it's going through like all the training, all the trees, and when you see that you don't improve accuracy anymore, it's stopping automatically, and so you always get the best number of trees. So you don't have too many of them, as that was the risk before. I still need to specify the number. So the number of boosting rounds, so that's my N estimator from before. Here I decide on purpose to put it really big, because I know that if everything goes well, I will never reach that amount. It will stop before. And last thing I need to specify is the number of folds in my cross validation. So if you're not familiar with cross validation, I'm just dividing my data set into like sub data sets and training on a certain amount of folds and testing on the other one. You can read up on that if you're interested. And finally, I'm specifying a seed as well, so I can get the same results as before. So it will run for a bit. As you can see, the star here specifies running. Let's check the result of that. So it returned a really nice data frame where the index here is the stage, so the index of the tree. So when we have one single tree here, the first tree, I get the train error and the test error here. I also get the standard deviation. I get the train error here, the test error here, and the standard deviation of each. And it goes down to the last tree that it built, where it was still decreasing the testing error. So after 25 trees here, I stopped improving my score, so there was no point continuing. So I can also really easily plot that, and I think it's a really interesting chart to look at. So I start from one single tree, and the error there, we see that the training and the test error are decreasing really quickly when you add more trees. Then the testing error is starting to stabilize a bit until it doesn't decrease anymore. Right. So again, now that I know my best parameters, I can train a new model. So I need to pass it my parameters, my training data. So let's call it XGB model. My training data, and here I need to specify the actual number of boosting trees that I need, my N estimators from before. So in this case, it's 25. Right, so now I have my model, so I'm able to make predictions. So let's use XGB model predict on my test the matrix, and let's check my score spread test. Right, so here it's quite a nice improvement, 3.26. So I'm 3.26 comments off on average. So I think that this could be improved more by decreasing we're probably improving the parameters that I've selected here, and also decreasing the learning rate and retrain it. And again, here I'm not gonna go through it, but you can again plot the importance of your features like exactly the same way we did before. Right. So that's it for XGBoost. So the next and the last library I wanted to show is a more recent one, and on many benchmark, it has beaten performances from XGBoost. So a lot of people start to use it for machine learning competitions. So that's definitely a library to look at if you're interested in increasing your performances. Also, in some cases, it trains faster. So let's import it. It's called LightGBM. So let's import it as LGB. And again here, I can import with the scikit-learn API. So that will be exactly my .fit.predict as before. But it has a native API that I'm not going to show here that allows more and like more features. Right. So here we can import either classifier or regressor. So I want a regressor here. Again, I've defined my my parameters before. As you can notice, those parameters have exactly the same names as XGBoost, so it's quite handy. You don't need to. You can easily switch from XGBoost to LightGBM without like relearning a whole new process and everything. Right. So now that I have that, I'm gonna create again a new grid search with my LGBM regressor as main model with my fixed parameters. I'm going to add my parameters for the grid and jobs -1, and my scoring I'm going to use again the same one. Here. I will now fit my grid search on X train, Y train. I see that my best parameters as I expected them to be. So now I will retrain a new model with those. So LGB model would be equal to my fixed parameters and the best parameters for my grid search. Right, so let's fit this model. X train, Y train. And now I can predict exactly the same way as I was doing before. So that's probably something that is worth mentioning. Like, it's really easy when you're familiar with scikit-learn to use those two libraries, just because they provide this really, well, the exact same API, so fit, predict. So now I can generate predictions directly from this new model using my X test. And I can calculate the error test. Right. So this is quite disappointing. You see that the error here is higher than with XGBoost. I think it's because we haven't gone through like too much tuning with LightGBM. Also, the learning rate could be decreased and improved. So I wouldn't go. I wouldn't say that it's because it's less performant. I think it just needs more work. And actually, that's a good point as well. That those two libraries, XGBoost and LightGBM, would usually need more work to be able to get good results from them. But it's usually worth worth it. Last thing that I wanted to show is that LightGBM also implements plot importance and plot tree. If you want to explore a bit and dive in your model, so here I can pass my new model and specify the importance type as being the gain again. For the same reasons as mentioned before, I will need to define my own figure. GCA. All right. So here we see that it's actually quite similar as before. X31 is the feature the most important, and we have pretty much the same thing. And exactly as before, I can just plot tree at GP model. Oops, I need to specify. Well, by default, it will take the first tree, but I can specify tree index for 0. Yeah, here's my tree. I will need to plot a figure if I want to make it a bit bigger. X equals CA. And here we are. So that's quite a nice tree. We can't really zoom in here. So same thing, you'll need to save it as an image to be able to zoom properly and see different nodes. But that's it. And again, LightGBM has a native API as well that would allow more advanced features. So check it out. Right, so I have a few notes to recap what we've said and what we've seen is this notebook. So first, scikit-learn is quite easy to, well, the random forest from scikit-learn is quite easy to tune, and it gives usually good performance. So that's a good model to start with, and like building a baseline and start seeing like what kind of score you can get. If you want to try to have better performances, it's usually worth looking at XGBoost or LightGBM. That gives better performance, but take more work to actually tune. And you should as well check the native API if you want to have more advanced features. If you want to have access to more content, you should check out our website that is right here at cambridgespark.com. You see how we have tutorials right here that explain XGBoost, but also other libraries or other concepts. We have other webinars that you should check if you want to learn more about pandas, EDA, or Spark. We have the bootcamp if you want to learn more in-depth things. So the next bootcamp is in September. You can apply now if you're interested. And we have conferences coming as well in Cambridge, London, and Manchester, so you can check that out as well. All right, thank you very much. Hope you enjoyed the webinar.